pen to read this? Okay, Bismillahirrahmanirrahim. Today we will deal with about the. Okay, let's see that data physical layer. There are a lot of things to read. We are not finished like switching and all, right? But today we move on to the next layer. What is that? Data link layer. In data link layer, a lot of things to do. We will read that, but the basic funda or lot of things in it, like framing and all. We will do one thing today because other guys are not here, so I have to recap it anyways. So we will do one part of it. That's called error detection and correction. Error detection and correction is done in the data link layer, and also it is done in a transport layer, right? So error detection and correction is done in the data link layer as well as in a transport layer, right? So if we say we will read the general chapter, error detection and correction, and then we will see where it is applied. So I'm not going according to the data link layer actually, because I will start it after 3-4 days maybe, the data link layer as a topic, right? Here I am going for a general topic, that is error detection and correction. Okay, so that is also part of data link layer, also part of transport layer. So I will better say error detection and correction. Let's say error detection and correction, we have in it Lrc, Lrc, Crc, and checksum. These are some techniques. These three guys in fact, are being done in the data link layer. And this one is done in the transport layer. Okay, so we are reading about error detection and correction, and in error detection and correction we have Lrc, Lrc, Crc, and checksum. These three are being done in the data link layer, and this one in a transport layer. Now, what is Lrc, Lrc, Crc? The Lrc is vertical redundancy chuck, and Lrc is longitudinal redundancy code or chucks. We can say it's a codes, vertical redundancy code, longitudinal redundancy code, and cyclic redundancy code. And then we have a checksum. Let's today have a grasp on it. You already have done about Lrc and all, Hamming distance and all. We have read it previous year, is it? So I will skip that part. I will only tell you the intro. We have done all that Hamming distance and how to correct and all those things, right? Error detection and correction last year. Do you remember that?
Yes.
Okay. Here we will say a little bit vertical. First is Lrc, that is vertical redundancy code. We here do everything with the redundancy. What is redundancy? Something to add more. What your data is, look, one way of dealing with errors is you send a data, right? And if you detect that error is there, if some error is there, for example, then you resend it, right? You resend the data. One way of doing it is that thing. That you ask for acknowledgement that has it reached or not. Even in that case, we have to detect whether error has occurred or not, right? We have to detect some way that error has occurred. So detection is still there, and if we don't correct it, we have to resend it. So better is we can also correct. For correction, we need to know which bit is an error. Exactly which bit is an error. If we know that this bit is an error, if this is 0, I know this is now 1. If it is 1, it's now 0. I do not have to resend the whole data. So correction is very important. Even our RAMs in the servers come with the error correction code ECC. They are very costly RAMs which has the error correction code. They not only detect error. One is something that error has occurred. Why it has occurred, which bit is in error, we don't know. But we at least have said that error has occurred. Like our Bhatt Sahib. When he was after the Imam Subh se galti gayi. He know error has occurred, but he don't know what is the correction. So he said what in the Salah? Galat, galat, wapas, wapas. He said it. This is true, this is a fact. This is not just a joke. He said it. But what he applied, if we see in our terminology, what he applied is error detection, not correction. He don't know what is correct. He said galat, galat, wapas, wapas means what? Retransmit. Means again you said it again. You repeat whole thing, right? So that's error detection only. He know errors occurred, so he has given some warning. Oh, something is, but he don't know how to correct it, right? He don't know the exact thing. So he should have recited the exact thing. Maybe Imam Sahib has done recited the same thing. But what he did is he said galat, galat, wapas, wapas. So what does that mean? Detect. Yeah, he detected error, but he said retransmit. That is a detection. In correction, we don't have to retransmit, rather we can correct. We are able to know which bit is in error exactly, so we can correct it. Right? So in the error detection, first these things we are doing. So we want to detect error. So that is the DRC, vertical redundancy code. It is simple parity. And it's redundant because we are adding some bit to it. We are adding some bit, right? So we are adding some bit to it, and in addition to our data, we are adding some bit. Okay? So what does that mean? That's redundancy. You guys get serious. We add something, a parity bit. It's like this, listen. If we have, for example, data is 1 0 0 0 1 1, and I add a parity bit to it. Parity can be even or odd. Listen, if it is 1, 2 and 3 ones are here, it is, and I have the even parity. Okay? What? Exactly. If we have even parity, we have to make the number of ones even. 1, 2, 3. So 1 makes it even. So total number of ones now, this is my data and this is a redundant bit, a parity bit. The total number of bits are even now. And if I send it, tomorrow some error occurs, this 0 becomes 1. And I'm not, this is an error this time. But I don't know when I send, I don't know this is an error. But when I calculate the number of ones, 1, 2, 3, 4, 5 at receiver, the number of ones are coming as odd. So this is an error. Because my number of ones should be even. You tell me, if I have 1, 0, 0, 1, 0, 1 and 1. This is my data, for example. So what parity I should add? If it's even parity? It's already even, so I should make it 0 here. So total data is this thing. The number of bits, number of ones are always even. Now when the number of ones are even, I don't have to add parity 1 because I have to make it even. When I send it, what will happen when I send it? I have to check again the number of ones. Are you sleeping? I have to check again the number of ones, right? So number of ones again here. If there is no error, number of ones will come be 1, 2, 3, 4. It's even, so it's correct. If they come odd, like for example, this one has changed to 1, so this is an error. So 1 bit, if it is a 1 bit error, it is gonna check. It can detect. I don't know why it is which of the bit is in error. But I calculate number of ones 1, 2, 3, 4, 5. Oh, odd. It's what? Error. Same is with the if we have odd parity. Then I will make number of ones as odd, not even, and check odd check in the right. Getting me? Now, if we have 2 bits in error, For example, this was as even parity. 1, 2, this was 0, 1, 2, 3 and 4. So this is even and we added parity with 0. Now 2 bits are in error, for example. Now this bit gets in error, this becomes 1, and this gets in error, it becomes 0. 2 bits in error. And my parity is even parity. What I will see? When I calculate at the receiver, when I calculate number of ones, that is 1, 2, 3, 4, that is even. It's correct, but it's not correct. 2 bits are in fact error. Right? So 1 bit error can chuck, but 2 bit errors it will not chuck. But 3 bit errors it will chuck. See, if you have 3 bit errors, now this bit is also in error. Number of ones becomes 1, 2, 3, 4, 5. Odd, so it is an error. So 3 bit errors will chuck. 4 bit errors it will not chuck, because 4 bit errors will again make it even. 5 bit, so 5 bit, 7 bit, 9 bit, so all odd bit errors it will chuck. Right? So all odd bit errors will be checked. जितने भी odd bit errors हैं वो सारे check हो जाएंगे. Right? Getting me? All odd bit errors will be not checked, I mean say detected. Will get detected. Right? So your all odd errors will be detected. In case of even parity, in case of odd parity, all
odd even bits. Odd bits.
Again odd bit, not even bit. Again odd. अगर हमारे पास odd parity है, if we have odd parity, again the same situation happens. It's an odd parity. कि हम number of ones odd रख रहे हैं. जैसे मेरे पास डेटा ये है. अब कितने ones है मेरे पास? 1, 2, 3, 4, 5. So what should be the parity bit? 0. Total number of ones should be odd. अगर एक बिट एरर हो गया इसमें, मान लीजिए ये 1 था, ये 0 बन गया. At the destination we calculate 1, 2, 3, 4. अरे ये तो even है, हमें odd होना चाहिए, तो ये एरर है. लेकिन अगर 2 बिट एरर में है, so number of ones 1, 2, 3, तो odd है ही. हम सोचेंगे कि हमें लगेगा कि एरर नहीं है, but एरर है. In fact 2 बिट्स का. Again अगर 3 बिट्स का एरर हो गया, ये 1 हो गया. Number of ones become 1, 2, 3, 4. That is even. Even means error because we have odd parity. Right? Getting me? So again, all odd bit error will be checked. Because odd parity हो, even parity हो, अगर एक bit error होता है, वो odd को even बनाएगा. अगर even को odd भी बना सकता है. ठीक है? एक bit error. 3 bit भी वही करेंगे. Odd को even, even को odd. ठीक है? अगर odd parity है, ठीक है? मुझे odd चाहिए 1 bit, 3 bit, 5 bit. ये सब इसको इवन बनाएंगे, तो हमें एरर डिटेक्ट होगा. लेकिन अगर इवन पैरिटी है, उसमें भी 1 बिट, 3 बिट, 5 बिट, 7 बिट, यानी कि ऑड बिट्स ऑफ एरर्स एरर डिटेक्ट कर सकते हैं. दे विल मेक इट इवन. सो अगर इवन पैरिटी है, दे मेक इट ऑड. सो मींस दैट ऑड बिट एरर्स will be detected, but all even bit errors will be skipped by this VRC. Getting me or not what I'm saying? So this is a vertical redundancy code or chuck. We sometimes call vertical redundancy chuck. That means that you add some parity bit, but the power of this is we can basically this is used for single bit error. What? Not for all other errors, because even bit errors will be skipped, odd bit errors will be taken off, but we will not use it for, because all even bit errors will be skipped. So this will be used only for a single bit error, not double, 3, 4 bits and so on. Only single bit error. And this will happen mostly when we have parallel transmission. Like if we have one parallel transmission, we have 1, 0, 1, 0, 1, 1 to send. We send it in a parallel wires like this. Look here. We send a parallel wires like this. And if one of the wires is in error, if there is some noise in one of the wires, for example this, it can change it to this, and we will get it. And the parity bit is at the end, right? Here is the parity bit. Well, that's why we call it vertical. Sometimes you say it's a horizontal or it's vertical, because basically it is like this. The data we send is in a parallel wires, and the last parity bit is here, right? This is the parity bit. How many bits they may be, 8 bit or whatever, but this is the parity bit of that. This is a vertical redundancy chart, right? And In these cases, 1 bit error is a chance. There's a chance of 1 bit error only. Only out of them maybe only one wire is an error. But if it's a serial transmission, what we usually have these days, a serial transmission, in which we have only a single wire, in which we send this data, right? 1, 0, 1 and all, this is sent here. And they go from here. If this wire is an error, we will not have a single, if there's a noise burst comes in. Noise is coming in, noise. It is changing some bursts. It changes some, not only single one bit, it may change many bits, right? So a burst error will come. In that case, we can't use the VRC. It's the simplest, and mostly use it for parallel transmission, right? Even in parallel transmission, we don't use it. It's a very simple. It was something to begin with. It was the basic thing, because it can chuck me only 1 bit error, and usually errors doesn't come in for 1 bit. It comes for a burst. It comes for what? So I want to detect that. So for that we have the LRC, longitudinal redundancy chuck. Okay? And LRC comes in the, you getting this any confusion? You have read it previous year also, so I think this is easy. In LRC, what we do is longitudinal redundancy chuck. And what we do here is we divide our data into rows and columns. For example, we have 88 bits of data. 88 bits of data, it's having some 88 bits, right? And we divide them into the rows and columns. Okay? For example, my data to be sent is 1 0 1 0 1 0 1 0 1 1 1. Like this is my data to send. I divide it, say, for example, into 88 bits, or for the simplest case, I will take 4 bits, right? 1 2 3 1 2 3 4. This is my 1 4 combinations, another 4 combination, another 4 combination, another 4 combination. Maybe it's like this. Say for example, this is my data to be sent. What I will do it, let me cut off for the simplicity's sake, let me cut off these two, make it a little simpler. Okay? Now what I will do here is, there's a 2 versions of LRC. LRC has a 2 version. One which is purely LRC. Second, it's a combination of LRC and VRC. Okay? What's called as 2-dimensional error detection. It's called 2-dimensional error detection. What's called? So in LRC we have basically 2 versions. One is the pure LRC, and second is 2-dimensional, in which we have LRC plus VRC, both. Combination of LRC and VRC. I will show first the pure LRC. What is the pure LRC? We do what? 1 0 1 0, then it is 1 0 1 0, then it is 1 1 1 1. I'm putting them in a columns. Okay? Then 0 1 1 0, then 1 0 1 1. Right? So I am putting them in the columns. Now what I will do is, for every column, I will chuck a parity on a downside. For every column I am chucking my parity, right? Understood? Okay, I didn't like that, please. Right? So this is me here. Not making good diagram. So what it will be, if it is an even, I will go for an even parity. What will be even parity of this column? 0. 1 2 3 4, so it is 0. What about this? 1 2, it is 0. What about this? 1 2 3 4 5, it is 1. What about this? 0. Again, it's a redundancy. It is R in it, because this was my data, but I have to send also this one. So I will send this one, and at the end I will also send 0 0 1 0. And this guy basically is my this redundancy code. This is my LRC. This will be my LRC. That I will also send with it. So I will not send only the data, but I will also send the LRC of this. And now this 0 0 1 0, this is not a 1 bit. These are 4 bits, right? For this depends on 4 bits, because I have taken 4 bits. If I have taken 88 bits, this will be 8 bit. So I have to send it again, redundant code. LRC with my actual data. Now this guy is for everybody, every column, right? So this is a parity for every column. So when I said it, if some error occurs here, 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 if in 4 bits no error occurs, this was my data, and if in these 4 bits somewhere the error occurs somewhere, you can check it for the parity, isn't it? अगर इन चारों में से किस कहीं अब एक बिट में नहीं, अगर चारों बिट में एरर है या 2 बिट में 3 बिट में एरर है, ठीक है, तो यहाँ तो पैरिटी गलत आ जाएगी, right? So we are able to detect errors not in a single bit but in 4 bits now. अगर 8 bit का मैं लेता, I could have detected errors for the 8 bits, right? But it will skip the error अगर एक ही कॉलम में 2 बार एरर आ गया, है ना? अगर एक ही कॉलम में 2 बार एरर आ रहा है तो ये स्किप करेगा, मान लीजिए ये 0 बन गया, ये भी 0 बन गया, ये पैरिटी तो ठीक है, 1 2 ठीक है, दैट विल बी स्किप. अगर एक ही कॉलम में 2 बार एरर आ गया, इट विल स्किप. अगर 3 बार आ गया, इट अगेन गेट इट. अगर 4 बार आ गया, अगेन स्किप. 5 बार तो ऑल इवन जो इवन पैरिटीज है वो स्किप कर जाएगा, अगर लेकिन एक ही कॉलम में, एंड दैट इज द रेयर चांस. अब यहां देखिए, look at the board. चलो बाद में लिखेंगे. That's a rare chance. Why? Because when the error comes, it comes in a burst. It will, when the error comes, it can destroy this piece of code. It's not. It is a, क्योंकि ये वाला और ये वाला फर्स्ट बिट जो है ना, ये कॉलम बनाती है. It is a rare chance कि इस बर्स्ट के पहले में आ गया, इसके भी बर्स्ट में, इसके भी पहले में, इसके भी पहले में एरर आ गया. It's a very rare chance. जब एरर आता है, it comes in a burst. Means it can destroy this chunk of code. So first हमने 8 bits लिया था. कितने 8 आ रहे हैं? 1 2 3 7 4 5 6 7. First this is 8. It is a rare chance that कि इसका पहला बिट और फिर उसके बाद इसका पहला बिट डिस्ट्रॉय हो रहा है, उसका पहला, क्योंकि वो आप एक कॉलम्स बनाएंगे ना, right? So it is a very good chance that if an error comes, it can destroy this whole chunk, and that can be treated because these will not come in a single column. इसकी पहली बिट एक कॉलम में आती है, इसकी पहली बिट दूसरे कॉलम में, इसकी पहली बिट तीसरे कॉलम में. मींस कि अगर ये वाला इसमें कोई बिट खराब हो गई तो कॉलम में से एक ही बिट खराब होगी, इस कॉलम में से एक ही बिट खराब होगी, एरर में होगी, एंड वी कैन डिटेक्ट दैट इजी. यू आर गेटिंग दिस और शुड आई रिपीट दिस? रिपीट? यू डोंट अंडरस्टैंड दैट? व्हाट आई एम सेइंग इज कि हमने जो ये 4 बिट्स का रखा, ठीक है, 4 बिट्स में ये पहला बंदा जो है ना, ये है, ठीक है ना, ये 4 बिट्स यहाँ है, तो ये इसका पहला यहाँ है, इन 4 बिट्स का ये पहला यहाँ है, इन 4 का ये पहला यहाँ है, सो ऑन, राइट? और मैं इस कॉलम की एक्चुअली पैरिटी देख रहा हूँ. दैट मींस मैं देख रहा हूँ इस पहले की, इसकी पहले की, उसके बाद मैं दूसरे की देखूंगा. दूसरी बिट जो होगी वो ये है, हर कॉलम एक कॉलम में, है ना. ये तीसरे कॉलम, ये कौन सी, कहां की बिट होगी तो बताओ? ये जो होगी ये 4th बिट है हर एक की, है ना. सो व्हाट इज इन माय कॉलम? First bit of every chunk which we have taken. If it is 4 4 or 8 bit, what will be here if I have 8 bits? ठीक है ना. पहले कॉलम में कौन होगा? पहला बिट हर एक 8 बिट चंक. दूसरे कॉलम में कौन होगा? दूसरे बिट. मैं ये कह रहा हूं भैया कि आपको जब एरर होगा वो बर्स्ट में आएगा, वो ऐसे नहीं आएगा कि इसकी पहली बिट खराब होगी, इसकी पहली बिट खराब होगी, इसकी पहली बिट खराब होगी. इस तरह अक्सर एरर नहीं आते. This will be a very rare chance. When the error comes, like how the error comes, a noise burst comes in. A noise आ गई, कुछ आ गई, हाँ? Noise आ गई आपकी वायर के बाहर, and it destroyed a chunk of, आपके एक चंक को इसने destroy कर दिया. That chunk will be like this. Maybe these 8 bits are an error. If these 8 bits are an error, they are actually in wire, in 8 columns. अगर ये 4 bits से error थी, ये 4 columns में. That means this whole column will be in error. No problem, because अगर ये 4 column error में है, we can detect the parity. Single bit error हो जाएगा ना, that can be detected. हम कह रहे थे किसमें ये डिटेक्ट नहीं करेगा कि अगर एक ही कॉलम में 2 बिट्स एरर में है, फॉर एग्जांपल, वो एक ही कॉलम में 2 बिट्स कौन होती है? ये और इसकी पहली बिट, फॉर एग्जांपल, ये एंड इसकी पहली बिट. You guys also listen here. computer organization architecture, we have the error detection correction, right? This is today's topic on that. You will also concentrate, okay? Sit and concentrate here. Little bit parity skip ho gaya aapko, but still you can get it. I hope so. We'll read it when we read it, but that is the idea. Are you getting my point when I'm saying, Samir? What? That if error occurs in a burst that will affect this will be detected, no problem. But if error occurs in this bit, say for example, and this bit, for example, that's a 2-bit error. Because these both are in a single column, then it will be skipped. Like we have parity before we said, VRC. Right? So that will be skipped. You're getting me? But I am saying that errors will not come like that. Errors will come in a burst. So that will affect this piece of code. That will affect either this burst or this burst. They will detect it easily. In the 2-dimension, what we do is, this was the pure LRC. In 2D, what we do is, we also do the column row check. We see the parity also here, the row check. That means this guy. 1 0 1 0. Okay? How many ones? 2 ones. So what will be parity?
0.
So parity will be 0. What will be parity in this case? 0. What will be parity in this case? 1. Here? What will be here? What will be here? This becomes a complete package now. So I have a very strong error detection mechanism here now. Okay? Because if now there is, even in the same bits, listen, if I have a 2 bits error here, like here and here, right? मैंने ये गलत निकाली ना, ये 1 था पहले यहाँ पे, ये भी यहाँ पे 1 था, ठीक है? इसलिए हमें आ रहा था 1 1 1 1 0. यहाँ पे आ जाएगा 1 2 3 4, ये 0 आएगा, 1 2 3 यहाँ पे 1 आएगा. अब मैं एरर कर रहा हूँ इसमें, ये 0 बना रहा हूँ, ये भी 0 बना रहा हूँ, 2 बिट्स का एरर हो गया. ये तो नहीं दिखाएगा एरर. Now listen here. Will it show the error? It will not show error because 1 plus 1 is 2 ones है. जब 2 ones आपके पास है, it is already even, so it is even, showing correct. But what about this guy? What about this guy? 1 2 3. ये error दिखाएगा. 1 2 और ये 1 यहाँ पे है, वो तो गलत है. बोलो कितने हो गए? 1 2 and 3. यहाँ 0 होना चाहिए था लेकिन 3 है. उसका मतलब है क्या error है? कि जो यहां से, जो LRC जो यहां से आपको स्किप करा रहा था error, अब वो यहां से स्किप नहीं होगा. You getting me? It will not be skipped. It is a very good error detection mechanism. What we did is we broke these into chunks, right? And we calculated the column check as well as the row check. And this will be a very, strong error detection mechanism, but it will skip a very rare errors. वह जहां यहां से भी इसका बराबर आता है, यहां से भी मान लीजिए. अब यहां इनके 2 में हो गया फॉर एग्जाम्पल, अब इनके 2 में भी हो गया. ठीक है? तो उससे क्या होगा? अगर इनके 2 में भी हो गया, स्किप हो जाएगा. यहां पर ये भी 0 बन गया, ये भी 0 बन गया, ये 1 बन गया फॉर एग्जाम्पल. ठीक है? अब इसके अगर देखेंगे हम 1 plus 1 is 2, that is 0. ये ठीक है, ये पैरिटी ठीक है, और इसकी भी ठीक है. 1 plus 1 is 0 ठीक है. अब यहाँ देखो 1 plus 1 is 0, ये भी ठीक है. 1 1 1 is 3 plus 1 is 4, ये भी ठीक है. ये स्किप हो गया. ठीक है? But it's a very rare case when these kind of errors will occur. You are getting me? But still, this is not a complete picture. I'm telling you that. This is not a complete picture. Because this is a very strong error detection mechanism, but still it can skip, as we visualize here, some errors. Getting me or not? Should I repeat it? Anybody have a problem? Does it make sense what I'm saying? Correct? Then we move on to the next thing. It's called CRC. That is Cyclic Redundancy Code. Cyclic redundancy code. You two guys will not understand it, okay? But still, just put something in the brain. Later on, when you read it, you will understand it, right? So, what I'm saying, CRC, Cyclic Redundancy Code, is also called the polynomial code. What is it called? The CRC is also called as a polynomial code. This is not right. It is also called a polynomial code. Why is it called a polynomial code? It's called a polynomial code because it takes the numbers like polynomials. If we have, for example, a data of like 1, 0, 1, 0, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, maybe 8, it takes it as x raised power 0, this is x raised power 1, x raised power 2, x raised power 3, x raised power skipped 5, and x raised power 7. So it will take your data like this, right? In terms of a polynomials, it's very simple. Where there is a 1, it will take it, where there is 0, it will not take it. So this is my polynomial. The cyclic redundancy code first does, how it operates is, there's a modulo 2. Modulo 2 arithmetic. Your addition and subtraction है, that is done by modulo 2. Or division is done by log division, that is what it does. इसमें modulo 2 arithmetic ये कर रहा है, ठीक है? What is modulo 2 arithmetic? The addition and subtraction. It is not done like a binary addition and subtraction. You borrow or you carry. There is no concept of borrow and carry in modulo 2. In modulo 2, you have addition or subtraction, just do XOR. What is XOR, Sabri? Yes. Same bits पे 0 different way. What is in terms of A complement B something? XOR. It is A complement B or A B complement. Right? Because XOR means, what is the truth table of XOR? A XOR B. Should I write it like A XOR B? 0 0 0 1 1 0 1 1. So where will we have the ones?
1 0.
It is same 0, it's different 1, it is different 1, it is same 0. So this is A complement B plus A B complement. Right? So XOR basically means A complement B plus A B complement. This is actually equal to A XOR B. So what does that mean is, if we have something 1 0 1 1 for example, and we are doing 1 0 1 0 to it, so what will be addition of it? If you want to add it, it will be 1 and 0, what will be that? 1 same. This is addition. Subtraction, again XOR. Suppose we have 1 1 0 1 1, 1 0 1 0 1, whatever. What will be subtraction of it? 1 and 1? What is this? Yeah? Okay? Very good. Right? So add or subtract, XOR. This is called modulo 2 arithmetic. Not your binary. In binary, we have to borrow, for subtraction, and for addition, we have to do what? A carry generation. Getting me? So, this is the polynomial code which does is, what is the idea behind the CRC? First, let's understand what's the idea behind the CRC. This is very simple. Just XOR. What is the idea behind the CRC is, but for example, we have a 9 and you divide it by the 2. What will be that? 2 4 equals 9, remainder is 1. Now if you subtract the 9 by the remainder, what is that? Now what comes after the subtraction remainder is what is exactly divisible by 2. Because 9 minus 1 comes 8. The 8 actually is exactly divisible by 2. That means 2 4 equals 8 and remainder is 0. That means this guy exactly divides it. Now if the error occurs in a polynomial, we do same thing. We divide it with something, what is called as generator polynomial. I will tell you in a short meanwhile, in just a short time. What is generator polynomial? What we divide is about generator polynomial, what we divide with. And what we divide is our data. We divide it and then subtract the remainder from the data, and what is left out is exactly divisible. Now if the error occurs and we see we again divide at the receiver, we again divide and we see there is some remainder, means there is some error, right? Because now what is left out after my data is subtracted by the remainder, what's left out is exactly divisible by the generator polynomial. Okay? So that means if I now divide the generator polynomial, there should not be any remainder. But if there is a remainder after division, after reception, that means it's an error. We can detect an error. Basically, we have to detect error, right? So we have to first select some generator polynomial. We have to select some generator, and the generator polynomial is, you know, is predefined. The sender as well as receiver knows in advance what is generator polynomial. What's called as g of x, for example, generator polynomial. Say, let us say this will be 1 1 0 0 1. Okay, 5 bits I will take. Right? 1 1 0 0 1. This is my 5 bits. What will be polynomial code of it? X raised to 0, 0 1 2 3 plus x raised to 4. This is g of x. X raised to 4 plus 0 plus x raised to 0. This will be my you know, and you can write here 1. X raised to 4 plus x raised to 3 plus 1. There can come in a question that g of x is equal to this, or they can say this. Are you getting me? If they say this, you have to, from this you have to say this is 4, then this is 3, then this is 1 at the 0th position. Though there are 2 zeros in between. Right? Or if they give it like this, so it is like this. You can divide it with this. Right? This is in advance fixed. What is this? A receiver knows it, the sender knows it. Okay? Now second thing is, I have to divide my data with this. But maybe my data is not 5 bit. Is it? My data is only 2 bits or 3 bits, something lesser than the generator polynomial. Will it not create a problem? Yes, it will. Are you getting me? So what I do in the second step is, I add my data, the degree of this, the zeros at the end at zeros, because adding at the end zeros will not do anything to my data, but this will make it bigger than the g of x. This will make it bigger than the what? G of x. So what is the degree of this g of x? 4. 4 is the degree, the highest order. So I will add 4 zeros. I will add what? At the end of my data. Okay? So let my data will be p of x. Let that be equal to, it can say in a polynomial or it can say in a simple way. If it says in a polynomial, x raised to power 9 plus x raised to power 8 plus x raised to power 7 plus x raised to power 6 plus 3 plus x raised to power 1 and plus 1. So then what is my data actually? At the 9 there is 1, at the 8 there is 1, at the 7 there is 1, 6 there is 1, 5 there is nothing, 4 there is nothing, 3 there is 1, and 2 there is nothing. Then 1 there is 1, x raised to power 1 means 1, and 0 there is 1. So that means this is my data, right? 1 2 3 4 5 6 7 8 9. What is this? Plus something?
0 1.
This is 3. Hey, plus कहाँ से आ गया? 1 here, okay? 1 2 3 4 5 6 7 bits. 1 2 3 4 5 6 7 8 and 10. Right. So I have 10 bit of data. Maybe I have 10 bit of data or 8 bit of data or whatever, and this is my g of x, generator polynomial, which I have to divide this guy. And this is known in advance what it is. And this we don't know, any data which can come. I will divide my data with the generator polynomial. Before that I have to do what? I have to append here, how many zeros? The degree. 4 zeros. So that this is done because this time it is bigger than this. But maybe my data is not bigger, it is smaller. So when I divide it, I will add the 4 zeros at the end to make it bigger. This time we don't need, but sometimes if our data is smaller, we have to add how many?
4.
It is 4 because my degree of the g of x is 4. right? If the degree of g of x is 3, I have to add only 3 zeros. If g of x is 2, according to the question. So mind it, this is not what it is. You will add all is 4. You have to see what is g of x in a question. Are you getting me? So now let us start dividing, and dividing is done. Simple division, what we do in a binary, but addition and subtraction done by modulo 2 arithmetic. That means XOR. Let us start doing it. So what is the first step? This may be the first step to see what is the generator polynomial. The second step will be to add. In a second step, what do we do? We will add what? 4 zeros. 1, 2, 3, 4 zeros. Okay? These I will add to my data, to the p of x. Now I go g of x into p of x. Means I will divide p of x with the g of x. So I have to divide it. I will say this one 1, 1, 1, 1, 0. So let me rub it and do it quickly because it will be bigger. हाँ सर को बताएगा ये क्या है? मुझे बता यार क्या बोल रहे हो? हाँ 0 0 1 0 1 और एक 1 डेफिनेटली 4 0 होंगे किसके? g of x के. What is g of x? Now divide it simply. क्योंकि यहाँ पे 1 है इसलिए 1 से होगा. That will be 1 1 0 0 and subtract it. Now modulo 2 arithmetic. Modulo 2 arithmetic. 0 1 means 1. 1 0 means XOR. Forget about this last bit. Don't do this last bit, right? Last bit, skip it. Because this will be 0, just skip this 0. Getting me? And now this will come down as a 0. First bit is 0. So multiply with 0. Divide it with 0, right? 0 into this is all zeros. 0 0, what will come it? What is up?
0 0.
Okay, 1 0 you again.
1
Moment.
1.
Who is moment?
1.
Fast 2. Skip it. Right? Getting me? उसके बाद अब 1 आएगा यहाँ पे. बिल्कुल ऐसे एरो मार के दिखाना, ठीक है? अब चूंकि पहली बिट 1 है, 2 with the 1. When do 1 multiplication with it is same. 0 multiplication with it is zeros. 1 से करेंगे तो बिल्कुल वही आएगा. That is 1 1 0 0 1. Fast 1. 1 minus 1 XOR. Shadab. अबे तू बीच में क्यों बोल रहा है? 0 1 0. Now you tell me. इसको skip करेंगे. 1 minus 1 is 0, but skip that 0. Don't write it. Right? Okay. Now 0 आ गया. ठीक है? Now because this is 0, we have to do the 0. It will be all zeros. Right? And this will be what? 1 0 0 0. Is it? Am I right? And कौन आ गया यहाँ पे? 1 आ गया यहाँ पे. So 1 आ गया है तो 1 से करो. And this will be 1 1 0 0 1. Right? And this will be 1 0 0 0. And आपका ये वाला 1 अब नीचे आएगा. And again 1 से होगा. So that will be 1 1 0 0 1. And this will be here it will be 1 0 0 0. Right? Is it? What is Duster? Okay. अब यहाँ से कौन आएगा? 0 आएगा. अब 0 आएगा. So 1 से होगा. That will be again 1 1 0 0 1. Forget about that this is bigger than this. Right? The model 2 arithmetic. Don't think this is bigger than this, or what will happen? Right? This is bigger, no? But we don't have to do binary subtraction, we have to do modulo 2 subtraction. So just do it. What is this one? 1, 0, 0, 1, right? Am I right? I'm doing a little faster. So again, this 0 will come in now. Here. Again, this will happen to the 1. And this will be 1, 1, 0, 0, 1. Okay, so this will be 1, 0, 1, 1. And now this 0 will come in. Again with the 1. This will be 1, 1, 0, 0, 1. Now this will be what?
1.
All ones. And last 0 will come up.
1, 0.
So 1, 0, what will be that? Now 1, 1, 1, and 0. This is my remainder. Okay? Finish up all the bits doing. What will come the remainder? What is step third now doing? This was probably the step third. In step second we added the 0. In step third we started dividing. To calculate the CRC, this is my CRC. This is to be subtracted with what?
Subtracted with the generator.
So what will happen actually, these girls appended here. These girls exactly appended here. Because XOR means कहाँ जाना है? घूमने जाना है? Okay. You want to go? वापस नहीं आना शाम को? वापस जाओ. So getting me what I'm saying? Subtract this and this. So difference will be 1, 1, 1, 1, 0, 0, 1, 0, 1, 1 and 0, 0, 0, 0. इसको आप माइनस करना है ना ये 0, 1, 1. ये डिफरेंटली XOR करके यही आएगा जो है 1, 1, 1, 0. So this is what I will send. In this we will have this much of thing is actually your data, and this is your CRC, cyclic redundancy code. Now this you will send. Now if you at the receiver, listen first then you write. At the receiver, if you divide this guy with the g of x, you will see there will be 0 as a remainder. Right? There will be 0 as a remainder. Because this will be exactly divisible by the g of x. Right? So now what happens is, if there is an error, if some bit is in error, 2 bits or whatever, the bits are in error, right? We will, when we start dividing it with this, we will get a remainder. We'll definitely get a remainder, right? So that means there is an error. This is a very, very powerful, redundancy chart. What we do simple is, we have our data and we have a g of x, that's general polynomial. We add that number of zeros, the degree of that, and we start dividing the modulo 2 arithmetic. We see the remainder, this is the CRC, subtracted with this, it will get appended actually here at the end, the CRC, and send this. And now this will be exactly divisible with this, that means the remainder will be always 0. Now if some error has occurred, and you will see there will be some remainder. You just try out. Okay, try some arrows in it and try to divide it, and you will see all the time it will be having what? It will be having some remainder if there is an error. If the remainder is there, we are detected that there is an error. Are you getting me? So we are detected there is an error. So this is what's called as CRC. The last these three things, VRC, LRC, CRC, they are being done in the data link here. Now checksum is done in transport layer. That we will do next time. This time you will divide this with this and chuck it. Do it. But modulo 2 arithmetic, right? That's all.